It looks like we are now on recording our show. I hope everybody remembered to turn their clocks back an hour to come to class. And I hope everybody remembers to vote tomorrow. This probably, for many of you, is the first opportunity you've ever had to vote. Maybe, I don't know, maybe I'm saying, at least for a presidential election, maybe this is for sure the first time many of you have been of age, I think, to vote. So it's very important, I think. Everybody should vote. Very important election. You probably think you know who I'm going to vote for, but I bet you'd be surprised. But in any event, I think everybody should exercise their right to vote. I think it's a very important process. I think everybody needs to make a statement about what they think about what's going on. Okay, so enough political stuff. Last time we met, we didn't meet really technically because of the fact that for the umpteenth time this semester, we were hurricaned out. I did meet, though, as it claimed we were supposed to do. We virtually met, which meant I was here. I talked. I posted that lecture video. If you didn't happen to tune in that day, last Wednesday, I posted the lecture video. You can take a look at it. It's on the Moodle site for, I guess that was the 28th of October. Hope everybody got lots of good candy over the weekend. What else do we have to cover before we get going? No, I guess nothing. One more very important item on the agenda. That would be that we still have this remaining part of our second test. The last segment of the remaining part of that test is still open and available. It closes tonight at 11:30. So please make sure that you have completed test 2, part 3 by 11:30 tonight. I mean, it closes at 11:30. So if you have it, you're open, you're working on it and it's open and it becomes that time, it will automatically be submitted. So please make sure that you go out and that you complete that exercise. All right, so then what we spent Wednesday, looking at was molecules, and in particular, the very important class of molecules that are based on carbon. Carbon, as I intimated last Wednesday, is far and away the most essential and important bonding atom out of the periodic table, mainly because of its prolific ability to concatenate to itself. There is no other element on Earth with this ability to at least form molecules now, in the formation of molecules. And molecules are individual entities independent of others. Now, they might have interactions with others that makes them so that they're a little sticky towards one another, but they ultimately are independent entities, like gases, molecules in the gaseous state, molecules in the liquid state. They're independent entities. And when carbon is around other carbons, it has this incredible ability to concatenate to itself, not just in straight lines. It can do so in rings and lengthy chains, and it can do so in a variety of schemes of connection, meaning in terms of how many electrons are shared between the carbons to connect them together. So carbon, again, unlike any of the other 113 elements in the periodic table, has an incredible ability to play this connection game with itself. So then what this leads to is a wide variety of systems that can do all sorts of complex chemical processes that ultimately lead to this incredibly, not only just fascinating, but incredibly unbelievable, really, culmination in what we can call, simply put, life. What life is boils down to the basis of carbon chemistry. So, I mean, it's still not completely understood, every little nuance of it, but a large amount of the understanding of the so-called biochemistry of life is very well documented, very well understood. We're still unraveling the frontiers of this that's going to hopefully lead to improved treatments for diseases that we still haven't been able to eradicate or avoid or wipe out of our genetics. There's all sorts of things that are at the frontier of biochemistry that are exciting things that are yet to be done. And it begins with understanding and unraveling the chemistry of carbon. Okay, so what we did then was began to look at the hierarchy of carbon chemistry molecules. We looked at what we called alkanes. And when you have an alkane, the ane ending implies that the carbons are singly bonding, and what singly bonding means, as we discussed over the past couple lectures, is each atom shares electrons, not transfers, but shares. In the ion world, electrons are transferred, and you have cations and anions, positive and negatives. In this bonding scheme that atoms like carbon undergo, neither carbon can rip electrons loose from the atom that it's connecting to. They have the same exact desire to pull electrons. So nature doesn't allow one carbon atom to be better at tugging electrons than another. So ultimately, rather than fight a tug of war over electrons for eternity, they decide to share. Each carbon contributes into a sharing region between the atoms electrons. Now let's think of what this means. Carbon A puts an electron into the pot. Carbon B puts an electron into the pot. These negative charges allow the positive nuclei now to get closer together. Remember, the positive nucleus of carbon A should be repulsive to the positive nucleus of carbon B. But now, since they've antied electrons into a chemical bond, this negativity that they have piled between them allows these nuclei that should be repelling to get closer to one another than they actually should be capable of. This is what chemists call a bond, the allowing ability of positive repulsive things to connect together because their positivity is shielded by negative electrons between them. Okay, so in an alkane, each atom has kicked in an electron. There's two electrons bonding the carbons together, and then we can build a hierarchy of concatenated carbons. And we had a series of prefixes that indicated to us how many carbons were in the concatenation. And we called those alkanes, and they began with the prefix meth for one carbon, F for two, prop for three, bute for four, and then they were pretty standard after the first four: pent, hex, hept, oct, non, dec. So the prefix simply tells you how many carbons to concatenate, and if you attach an A and E ending, that meant single bond. Okay, after we discussed that, then we looked at the ones that double bond. When carbons double bond, they put two electrons connecting the carbons together each. Okay, a single bond, each carbon puts in one electron, a total of two shared. In a double bond, each carbon puts in two, so there's a total of four shared. Now we use the same prefixes to indicate how many carbons are in the chain, but we change the suffix to -ene. So instead of ethane for the single bonded two carbon chain, we have ethene, which is a double bonded two carbon chain. Instead of propane for a single bonded three carbon chain, we have propene, which is a double bonded two carbon chain. Okay, so that's pretty much where we ended up. And what I'm going to do now is maybe do a presentation of the slides from that point. I'm trying to get my thing to pop up here. Let me put, there's my present now thing. And I'm going to, of course, I have to say the words. So let me just say the words while I'm presenting. All right. So now I'm going to go to my PowerPoint. And this is pretty much where we left off. So let's go to that one. These are the so-called isomers of hexene. Okay, so let's digest the name. Hex means 6 carbons in the chain. Ene means there's got to be a double bond in there somewhere. Okay, now in this 6 carbon chain, though, where the location of the double bond is what creates the so-called isomeric forms. First, let's understand what the word isomer means. It means same atoms connected together, but you connect them together in a different way. So those are isomers. The formula for hexene is always C6H12. So that's the chemical formula of this connection of carbons and hydrogens. But it's a matter of where the double bond is located, which will differentiate one of the hexene isomers from another. Okay, so again, as a reminder, how do you build this hexene? Well, a line connecting carbons together indicates a pair of electrons. So what I need to do is put 6 C's in a line and put a connecting line between them, and that would mean they would all be singly bonded. That would be what I would use for hexane. But since this is hexene, one of the straight lines is going to now be a double bond line. So I can have a case like this. Okay, now let's indicate again what this particular isomer is showing. A line, again, connecting the C's is a bond. 2 lines is a double bond. 3 lines is a triple bond, and so forth. What does a bond mean? It means 2 electrons being shared. What does 2 lines mean? It means 4 electrons being shared, 2 for each line. So since this is a hexene molecule, there is a double bond in there somewhere. So the double bond on this case is between carbon 1 and carbon 2 if I numbered them from left to right. So that's why I indicate this as being 1 hexene. Now, the other positions that you see around the carbons, besides their connection in a line of 6 of them, is always in a hydrocarbon molecule connected to hydrogens. Now, for reasons that are not immediately apparent, of course, but would really need more detail than we want to go into, carbon always wants 4 bonds, always. The number of electrons it has around its nucleus cries out for 4 more electrons from somewhere else. So it shares electrons with other atoms to get the 4 electrons that each carbon in the universe is crying out for. So that means each carbon must have 4 lines touching it. If the line that is touching it is not connecting it to a C, it still needs electrons in those locations, so it shares them with H's in hydrocarbon molecules. So after I draw the straight line of 6 carbons and I put 5 single lines between them and I put 1 double line between the other 2, I have to connect to the remaining carbons present enough H's so that there are 4 lines touching each carbon. So that's what you should notice from the way this picture is drawn. Each carbon has 4 lines touching it, whether it's on the end, whether it's in the middle, or whether it has a double bond or a single bond. All carbons have 4 lines connecting them. So this indicates that the carbon on the end would need 2 hydrogens. The second carbon over needs 1. The 3rd, 4th, and 5th carbons need 2 hydrogens, and then the 6th carbon on the end very right end needs 3 hydrogens in order to satisfy the desire of electrons that they need to complete their structure. So this would be 1 hexene. If you count it all up, it would be C6H12. But also another way of doing this, as I talked about before, chemists like to write it out, almost literally telling you what the surrounding region of each carbon is like. So one hexene might also be written CH2, CH, CH2, 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 CH3. And that literally tells you how each of these are connecting to internally to build a 1 hexene. Now, as I mentioned, this is not the only way to build hexene. There are 2 other ways of doing it that use the same chemical formula, but have slightly different structures. And all these slightly different structures are doing is moving the location of the double bond. So I can move the double bond to position 2. And you'll notice that this is a different structure, but it's really the same chemical formula. Again, this is C6H12, just like the top molecule is C6H12. Now this one, though, if I was going to write it out literally, that would tell me the difference between this and the top one would be, I would name this one CH3, CH, CH2, CH2, CH3. That would be one way of indicating that this is a different isomer than the other one. Another way of indicating it's a different isomer is to put the location of the double bond. You'll notice to the far left, chemists will state that this would be 2 hexene and compared to the top one, which is 1 hexene. Now I can continue this theme by moving the double bond over one more spot. And if I move it over one more spot, I can have 3 hexene. And unfortunately, again, parts of this is underneath my little picture. Someone told me that maybe I can remove my little picture. I don't know. If I move that thing out of there, am I going to turn this off? I don't know if that will do that, if it'll turn it off if I move it. So I'm scared to do so. Let me see. Let me put my glasses on and look. It says hide. Why did someone tell me that this said hide? But if I hide, how do you get it back? Ooh, that's an issue. Oh, well, let's hide. What the heck? I'm hiding it. If I wanted to get that back, I have no idea to get that back, but it's hidden now, it says. All right, so this bottom isomer, again, has the chemical formula C6H12. But maybe if I wrote it out more to show more about the connectivity, it'd be CH3, CH2, CH, CH2, CH3 would be another way of writing it out a little more longhand. Now this one is also named 3-hexene because the double bond begins at carbon number 3. Now I do want to point out to you that if I were to continue this idea and make 4-hexene, you say, well, why don't you have 4-hexene or 5-hexene? Why are you only showing these 3? What I claim to you is 4-hexene is really 2-hexene, meaning if you put the double bond going between carbon 4 and 5, and then just flip the molecule over and reverse its direction, instead of being between carbon 4 and 5, the double bond would be between carbon 2 and 3. So what I'm claiming to you is 4-hexene is not unique. 2-hexene is exactly the same molecule, just kind of flipped over. Same thing is true if I decided to make something like 5-hexene. If I put 5-hexene, I'd put the double bond between 5 and 6. But if I did that and then just flip the whole molecule over, putting the right end on the left side and the left end on the right side, then the double bond will be between carbons 1 and 2. So you only name as many isomers as you can uniquely place the double bond. If you can flip the molecule over and put the double bond in the same location as it was in another of your pictures, then you don't call that an isomer. Okay, so there are actually then 3 isomers of this hexene molecule that we're showing here. Okay, the next double bonded types of molecules. Now, maybe one more thing I should point out, and I guess I decided not to go into this because this is enough gore. We're not really here to get into this. We're just here to get the flavor of this, not really the gore of it, I would say. But what happens if there's more than one double bond? What happens if there's 2 double bonds? Well, we have a simple way of indicating there's 2 double bonds. I call it a diene. Di means 2 double bonds. If there are 3 double bonds in this molecule, I could call it triene. So I can have, for instance, instead of 1 hexene, I could have 1, 2 hexadiene. And that would tell you put a double bond at carbon 1 to 2 and a double bond at carbon 2 to 3. I could have 1, 3 hexadiene. Then I'd put a double bond from carbon 1 to 2 and a double bond from carbon 3 to 4. Okay, so I can have those kinds of isomers as well. I could have 1, 3, 5 hexatriene. So I put a double bond from 1 to 2, from 3 to 4, from 5 to 6. And then there's 3 double bonds, so that's a triene. Okay, so I decided we didn't need to go into all that gore, but this is an easy way in which you can indicate whether or not there are more than 1 double bonds in the molecules. But what I did decide to do is just show you pictures of what happens when there are alternating single and double bonds. These are a very important class of molecules. Turns out they have very important properties that result when there's every other atom is singly or doubly bonded. And this class of molecules has come to be known as aromatics. And the reason they originated as being called aromatics is that more often than not, they're stinky molecules. They have the characteristic of the way that they're attached to each other, that they give off very characteristic odors of molecules that I'm sure you're familiar with. Things that you smell like in paint, things that you smell in paint remover, things that you smell in fingernail polish remover. These are what we would tend to call aromatic molecules because of the distinct aroma that is very detectable when they're present. Now, the most famous of all aromatics is a molecule known as benzene, and it has the formula C6H6. And so what you should notice about benzene is the way that the atoms are connected are such that there are 6 carbons. So you would think we would call this hexene of some type, but we call this benzene mainly because this was used by humans for a long time before we even knew there were 6 carbons and they were hooked together in a ring. So much like I talked about with water and ammonia, this was used a long time before it was understood what it was. So its traditional name was benzene. So even after they learned what it looked like and they knew its bonding scheme, they didn't want to give it a name other than what it was traditionally called. So you can see here, benzene being C6H6, it is a series of 6 carbons in a ring like a hexagon, and every other carbon is doubly and singly bonded. And then in order to complete all the bonding requirements of each carbon, you'll notice each carbon in this picture has 3 lines touching it because it has 1 carbon that it's doubly bonding to, 1 carbon it is singly bonded to. So this pattern repeats all the way around the ring. Each carbon has 3 lines it shares with other carbons. That means it's sharing 3 electrons with other carbons. So as I talked about before, and as always the case, carbons want 4 electrons to share. So carbons all require 1 more electron. So I'm going to put another line with an H in the locations that aren't C's. So this will end up being C6H6, and it has this structure that we see here. Every carbon, now with the addition of the H's, we can see every carbon has 4 lines touching it. And again, this is the theme of all these structures. All of them are going to show carbons with 4 lines attached to them in every organic molecule that we deal with. Okay, just some more pictures of aromatics. These are called polycyclic aromatics. What I've done, I got lazy. I left the H's off. So all H's are it says all H's are emitted. That's not what I meant to say. All H's are omitted for clarity. Okay, so where would those H's be? Well, if you look on the carbons that all have 3 lines, you'd have to add an H on each one of them. Okay, so I didn't put the C's on these molecules or the H's, and this is very common what chemists do. We leave all the H's off. We don't even put where the C's are, but we just draw the line pictures that show how the carbons are connected. So with my little cursor here, I would say I would need to put an H up here, put an H there, put an H there, put an H there, then come over to this one, put an H, an H, an H, an H. And then that would make these completed structures of these so-called polycyclic aromatics. So polycyclic aromatics have this alternating single and double bond, and they have polycyclic, meaning more than one ring. Now, it turns out that the chemists and astrophysicists even are looking through outer space to locate the signature of these molecules. Now, what does that mean? If we shine certain frequencies of light into space and look which frequencies of light are absorbed by materials in space, you can get an idea of what molecules are present by what kinds of light are absorbed by materials in space. So astrophysicists are searching the heavens for the appearance of molecules of this type. Why are they searching the heavens for appearance of molecules of this type? Because when you start to have molecules of this type out there in space, these can be combined in the correct fashion to make living systems. So they're looking for things like this in order to get some idea if there's a possibility that there may be some living systems out there somewhere other than on this particular planet. Okay, so really all I wanted to do was show us some things about the polycyclic aromatics. We're not going to get heavily into the details of them. What I will point out again though, is that these are molecules that have alternating single and double bonds. What I do want to do is spend a little bit of time with the systematic naming of what we call alkynes. Now, alkynes are just continuing everything we've talked about before. When we talked about alkanes, they had single bonds. When we talked about alkenes, there was carbons with double bonds. Now when I talk about alkynes, they're going to be carbons with triple bonds. Now, in particular, if it only has one YNE ending, then it's one triple bond. If you have diwyne or triwyne or tetrawyne, then you're going to have 2, 3, or 4 triple bonds in the molecule. But anytime you just have YNE, that means somewhere in the connection of the carbons, you have to let a carbon triple bond. Now, what does it mean to triple bond? Each carbon kicks 3 electrons into the share zone. So alkynes are hydrocarbon chain molecules which one or more of the C's are connected by triple bond or connected by each atom kicking in 3 electrons to the share. So what we do for alkynes is name them exactly the same way we would have done for alkenes or alkanes. You put the prefix that tells you how many carbons are in the chain. Then you put the YNE ending. That's all you do. So if there's more than one bond, then you indicate where, or if there's isomers possible, you indicate the location of the triple bond. Okay, I'm showing the general formula there at the bottom, but let's just take a look at them and we'll be able to see what the general formula is when we count the carbons in the structure. So let's look at the simplest possible or alkyne molecule, and it's not methine. Methine would imply you have one carbon in the chain. Well, you need two carbons in order to get the triple bond. Carbon cannot triply bond to H. So carbon only singly bonds with H's. Again, to know and understand the gore of that, you have to know a little bit deeper, you have to have a little deeper knowledge of why H only wants one electron. But let's just take it at face value. Hydrogen only ever single bonds. So there will never be an HC double bond, an HC triple bond, or definitely not an HH double bond or an HH triple bond. So hydrogen is only going to single bond. So methine can't exist because there's only one carbon in a molecule that uses the prefix meth. The simplest possible alkyne must be ethyne, which has two carbons for the F prefix. I will triple bond the carbons together, and then when I do that, there are 3 lines connecting the C's. Now, that means that since, as usual, all carbons want 4 bonds to share electrons with them, each carbon, if after the triple bond is formed, still needs another bond. And since there's only 2 carbons in the chain, if there were more, I could put carbons there. But since this chain only has 2 carbons, I have to attach H's. So I'm going to attach H's in the location where the carbons, after I put the carbon chain together. So this is the chemical formula of ethyne. Now, there's a common usage name for this that comes from, again, a long time ago. And the common usage name for this is acetylene. Acetylene is a molecule that has traditionally been used, connection of carbon that is used in welding and in all kinds of use of high energy fuels. Acetylene is a very high energy molecule, as we'll talk about shortly here. And when it burns so hot that you can melt metal. So acetylene has been used for 100 or 200 years in welding processes before, most recently, in the last 20, 30 years, we've been able to build electrical welders that use electricity that are a lot safer. If you had to carry tanks of acetylene around, they can be very dangerous. So now people who work and fabricate with metals would really prefer to use arc welders, which are electric welders, mainly because for safety reasons, you don't have to deal with carrying tanks of acetylene around, which in many instances have been found to be highly explosive. Okay, so acetylene would be a 2-carbon chain, triple bond between the carbons, and then since each carbon requires 4 connections, you're going to have to put hydrogens as a single bond to the other connections. Let's move to the next possibility. Okay, I said all those sorts of things. I'm not going to say them anymore. I will say that the formula for this, as you can see, is C2H2. Or you might write it as CHCH. And that tells you a little bit about the connectivity of it. Tells you how the H's are distributed around the various C's. Now, let's move to the molecule propyne. Prop means 3 carbons. Yne means triple bond. Now, for now, you might say, well, how come there's not 2 triple bonds in propyne? Anytime it just has YNE in the ending, there's 1 triple bond. If it said diene, there'd be 2. If it said triene, there'd be 3, and so forth. So propyne, I'll do this by putting the 3 carbons in a line, and then I will put the triple bond where it goes, like this. And then what I will do is put H's in the remaining positions. Okay, so again, prop means 3 connected. Ine means one of the bonds is triple. And then what you do is look at the C's and decide, do they need any more electrons shared? The C on the left has 3 lines touching it. It needs 1 more line touching it. That will be done with an H. The C in the middle already has 4 lines touching it. It doesn't need any more. The C on the right has only 1 line touching it. It wants 4 lines touching it. It needs 3 more H's. So what I will do is I will connect the H's as you see at the bottom here. This should be the completed picture for propyne. Now, some people want to call this 1-propyne, but that's okay. You can do that because it tells the location of where the double bond is. Some people do that. Some people don't. So I'm not going to argue the necessity of whether you have to indicate where the double bond is on this. I would say that it's done both ways in this particular case. But when you go to butene, that's when you have to be a little more careful. Butene, I thought maybe I would do that. You would have to do some indication about where the double bond is, because there are 2 isomers of butene. There's 1 butene or 2 butene. So you have to be a little more careful when you would build something like that. I guess I'm not going to do that, so it doesn't really matter if we do or we don't. What I do want to talk about are the difference between saturated and unsaturated hydrocarbons, because you might have heard this word before in a slightly different context that I will mention after I finish just looking over the words that are written on this particular slide. If you have a saturated hydrocarbon, it has the maximum number of hydrogens attached to the chain. So when can you get the maximum hydrogens? When all the carbons are singly bonded. When all the carbons are singly bonded, then you need more H's to connect to the carbons. So when you have singly bonded carbons and all the remaining connections are to H's, you call that a saturated hydrocarbon. An unsaturated hydrocarbon has 1 or more multiple bonded carbons. And in an unsaturated hydrocarbon, since some of the carbons have double or triple bonds, they don't need as many H's. So unsaturated hydrocarbons can be saturated if you do a hydrogenation reaction. Hydrogenation is adding hydrogen to the multiple bonds of the unsaturated hydrocarbon. Now, why I mentioned that in this context, and where your mom and them might have heard of saturated and unsaturated, at least those terminologies, is when we discuss in food and dietary materials things like saturated fats and unsaturated fats. Now, I know we have all somewhere, someplace come across that terminology. A saturated fat, and maybe we'll see this a little bit later, maybe not today, but or maybe even by next Monday, we will be looking at this a little more closely. But a fat molecule, it turns out, is just mostly a long carbon chain, mostly. So in a fat molecule, you're going to get a bunch of carbon atoms connected, concatenated over and over again. You're going to get a little other stuff too, but mostly it's going to be carbon atoms. Now, if it's a saturated fat, that means all the carbons in this fat molecule are singly bonded. That's all that it means. If you have an unsaturated fat, that means somewhere along the bonding of all the carbons in this fat molecule, there's a double or triple bond. That's what it means. If you have a polyunsaturated fat, I'm sure you've heard that term too, polyunsaturated fats. Polyunsaturated fats, poly simply means multiple double bonds. So there are multiple spots on the polyunsaturated fat that you have double bonds. Now, if you hydrogenate your unsaturated fat, you make saturated fat. Believe it or not, this is what you do to make something like Crisco or margarine. They take unsaturated fats, dump hydrogen into it, open up the double bonds and triple bonds, and connect hydrogens in those locations. And when you hydrogenate the polyunsaturated fat, it turns it from liquid into a soft solid that looks like butter. Okay, so very often we pull off these chemical reactions on fat molecules to take oils, and that's all, oils are just liquid fats, and make them into fats, which are actually solid molecules of much the same form. That's really, as we will maybe see further down the road, the definition of difference between, say, safflower oil, vegetable oil, coconut oil, or fat. Fat is solid forms of these molecules. Oils are simply liquid forms of these exact same molecules. Okay, so then bottom line, saturated fat has maximum hydrogens, meaning all the carbons are singly bonded. Unsaturated fat, somewhere along the long carbon chain of the fat molecule, there's a multiple bond that can add extra H's onto it. Polyunsaturated fat, more than one of these double bonding sites somewhere along the chain that can put hydrogens onto them. Okay, now let's just briefly say something about the energy of these carbon bonds. Now, unfortunately, we haven't talked energy yet. After we get done doing a little bit more with bonding here of the carbons and putting them together, I am going to spend a little bit of time on energy because it is so important to us. And we're going to talk about the energy stored in chemical molecules and how humans over time have learned to release the energy from chemical bonds. Okay, so it's really quite a simple relationship between how many carbons are the number of electrons shared between carbons in their connection and how much energy is present in the bond. Maybe first of all, we should recognize the fact that when we burn a fire, invariably the fuel we are burning is carbon-based. Now, not always, but I would say 99.99% of all fuels that humans use are carbon-based fuels. Now, oftentimes we call them fossil fuels. Fossil fuels are dug out of the earth and they're harvested out of the earth. But at some point, the material which has formed those fossil fuels was alive. Now, it could have been animate, but most likely it was inanimate, meaning these were big fields of trees and weeds and moss and things of that sort that somehow, in cataclysmic upheavals of the earth millions of years ago, got folded in and piled in to the earth itself, and they were squeezed and squished and pushed upon by the tectonic movement of plates of the earth and all this other stuff, and the pressure of all the earth piled on top of it has squeezed it in to a connection of carbon atoms that in no way, shape, or form anymore looks like a plant or an animal. It's puddles of oil and goo that are essentially hydrocarbon molecules. So any fuel that we burn, including wood, and also including, of course, gasoline and any of the other components of gasoline, or any of the other fuels that we might use, like propane or ethane is often used, natural gas, which is methane, commonly used. All these things are hydrocarbon molecules. So far and away, human fuels are carbon-based fuels. Now, equal important to the carbon-based fuel is the oxygen out of the air. Believe me, there's a huge component of the energetics of reaction when we burn materials. Of course, we burn materials to harvest energy. Well, there's a lot of energy that comes about from those because of the release of energy between the bonds of the fuel molecules. So when we burn the hydrocarbon, we're breaking the bonds apart, and in the chemical bonds, there is energy stored. Now, I want to make clear to you that it is not only the energy in the chemical bonds of the hydrocarbons that we're breaking, there's also a vast amount of energy in the bonds of the oxygen in the air that we're breaking. As a matter of fact, I might argue to you that the majority of the source of energy in the fire is not due to the breaking of the hydrocarbon bonds. More likely, it's due to the breaking of the oxygen bonds. Why? Because the oxygen bonds, you're breaking a lot more of them typically, and you're also breaking a higher energy bond. The O2 bond is a very high energy bond. But let's focus now on the energetics of the CC bonds. And what we will quickly understand and learn, if you study this a little more closely, is that the number of pairs of electrons shared by atoms is called the so-called bond order, and the potential energy, or the amount of energy that is stored in a chemical bond, depends directly on this so-called bond order. So if you have a triple bond and you break it, you are going to release the maximum amount of energy in the hydrocarbon molecule. If the molecule has double bonds, breaking those apart releases more energy than single bonds, but less than triple bonds. And in hydrocarbon molecules, single bonds that you break give you energy. They just give you the least amount of energy compared to the other two. So if I were to burn ethene, ethane, and ethine, all right, so let's get this straight. I'm going to build a fire, and as the fuel, of course, I'm going to need oxygen, because to burn something, oxygen is the fuel that is absolutely necessary. So then the oxygen from air will combine with something else. And for the other component of the fuel for the fire, let's use the 3 2-carbon chain molecules. And those would be ethane, ethene, ethine. So ethane, as the name implies, A-N-E, has a single bond between the carbons. Ethene, as the name implies, double bond between the carbons. Ethine, as the name implies, triple bond between the carbons. So when I'm burning these fires and using the same amount of fuel in each, I would find more energy can be harvested. The most energy could be harvested from the ethine fire. The second most amount of energy could be harvested from the ethene fire, and the least amount of energy from the ethane fire. Now, don't get me wrong, it's still plenty of energy. You're just going to be able to get much more from the ethine fire. As a matter of fact, burning ethine is hot enough to melt metal and then fuse it together in a weld. Burning ethane, it's hot, and believe me, it'll toast you up pretty good, but it's not going to be hot enough to melt metals. So that's why acetylene is used in welding, because acetylene has a triple bond between the carbons. So when you combine that with the energy released from the oxygen, it's so much energy that metal will melt. So triple bonds will store more energy, if you like, than will double bonds. Double bonds will store more energy than single bonds. And if I break those bonds, I can release that energy, harness that energy, harvest it, and then use it to do some processes that I prefer to do. Okay, so the bond order in a triple bond, we would say actually, don't look at that. Those things are actually backwards. I don't know what the heck. I must have been falling asleep when I wrote this. The bond order in triple bond is 3. That's the number of pairs of electrons shared in the triple bond. The double bond, yes, has a bond order of 2. The bond order in the single bond is 1. All right, so I'm sorry about that. I apologize. Again, a triple bond has bond order 3 because it has 3 pairs of electrons. Single bond should have bond order 1. It has 1 pair of electrons. Sorry, I apologize. When I make up these slides, sometimes I'm not thinking. Okay, now let's just say something about the volatility of hydrocarbons. Now, I mentioned volatility when we were talking last week. Let me remind you what volatility means to a chemist. It's a little bit different than what it means to your mom and them. If you tell your mom and them that you have a volatile material, they would immediately imply combustible. Volatile means burnable. So if I have some like gasoline is volatile. And typically what that means is it burns. You got to be a little careful with it when you're handling it because it can easily burn. Okay, so what does volatile mean to a chemist though? Volatile means escapable from the collection of molecules, meaning they evaporate and get into the air and stink really readily. Gasoline is volatile, but to a chemist, gasoline is volatile because it evaporates really easily. As soon as I open the gas can, I can say, ooh, I smell gas because it's escaping into the air and it's going into my nose and stimulating the detectors in my nose. When I open a can of paint, when I open a can of paint, you immediately sense the presence of that material because it's volatile. It escapes easily from the liquid phase and comes into the air and goes into your nose and you're breathing paint, as bad as that sounds. Same thing with fingernail polish remover as well, turpentine. These are volatile materials. Now there is some correctness to the point being that they're dangerous because they burn. It is the vapors of gasoline that burn. It is the vapors of paint in the air that would burn if there's enough paint vapor in the air. So volatility is tied to the fact that the vapors are the combustible materials that are part of it. But typically, though, volatile just means escapable. Why are they escapable? Because there's loose association of the molecules so they can get apart from each other easily because there's little intermolecular force holding them together. They're not very cohesive because the connections between them are not great, so they escape easily. Now, we say here on this slide that there's dispersion forces holding the molecules together. Those are very weak attractions that the individual molecules exert on each other to keep them into a liquid phase. So carbon-hydrogen bonds are not very sticky to each other. They all don't work together to pull on the molecules, so they are relatively nonpolar. They don't stick together very well at all. So as the size of the molecule increases, though, they get heavier and stickier. So the bigger the hydrocarbon molecule, the less volatile the molecule. So if they're big, they're going to be less volatile. If they're small, they're going to be more volatile. So the shorter the hydrocarbon molecule, the higher its volatility, the longer, the less volatile it would be. So if I look at these molecules, I'm going to pop a whole bunch of them up here. And we'll see what, let me back that up. I put them all up here at once. So I have methane, ethane, propane, butane, pentane, hexane. Remember, ane means single bond. So I have single bonds in every bonding position on these hydrocarbons. Meth means one carbon, eth means two, prop means three, but means four, pent means five, hex means six. So I have the 2 carbon, 3 carbon, 4 carbon, 5 carbon, and 6 carbon chains, and I'm showing the connectivity of the carbons together. So there's a single bond between 2 carbons in ethane, and there's 3 H's around it. There's a single bond between the 3 C's in propane, and then there's 3 C's on the 2 ends, 2 C's on the middle C. I said that wrong. There's 3 carbons connected, 3 H's on the 2 end carbons, 2 H's on the middle carbon, in propane. Now, on the far right, what I'm showing is the so-called boiling point. Now, what does it mean to be a boiling point? That's the temperature that they change from liquid to a gas. So the boiling point of these materials is, again, the temperature to take it from a liquid to a gas. Now let's go to the bottom ones. Now these are in degrees C, so again, that's a little bit weird for us. For instance, when it says pentane boils at 36 degrees C, if you ask me what temperature that is, I would say that's about 85 Fahrenheit. So at 85 degrees Fahrenheit, you can boil pentane. At 69 Celsius, you can boil hexane. That's probably about 90, let me back that up. 36 degrees Fahrenheit is, yeah, I'll go with it again. That's probably about 90 or so. 69 degrees C, that's probably about 110 or so degrees Fahrenheit. Remember, water boils at 212 degrees Fahrenheit. So if you wanted to boil water, you'd have to heat the water to 100 degrees C or 212 degrees Fahrenheit. So these all boil well below the temperature of water. The red dashed line indicates room temperature. That's 76 degrees Fahrenheit is 25 degrees Celsius. Somewhere in there would be room temperature, I would say. Notice that butane boils at about 0 degrees Celsius. That's about, that's pretty cold. That's about the freezing point of water. Okay, so butane boils right around the freezing point of water. So boiling means it's changing to a liquid where water is melting from a solid to a liquid. Butane is boiling from a liquid to a gas at the same temperature water is melting from a solid to a liquid. So that gives you some idea of the difference between the temperature to change the phase of these hydrocarbons compared to changing the phase of water. Notice propane, ethane, and methane, you have to make really, really cold. Now again, these are in Celsius, not in Fahrenheit. Actually, propane, it's kind of a weirdness of the Fahrenheit and Celsius scales. The point where propane is boiling at negative 40 degrees C is actually about negative 40 degrees Fahrenheit as well. So there's like a very famous, at least to scientists, crossing point of the Fahrenheit and Celsius temperature scales, and they're right about minus 40. So propane boils at about minus 40, either Fahrenheit or Celsius, but you'll notice to boil methane, for instance, to change it from a liquid to a gas, the temperature of the surroundings to boil it from a liquid to a gas only needs to be minus 164 degrees Celsius. I'm telling you, folks, that's cold. That's cold. It will boil at very, very low temperatures. So, okay, what should you take from this slide? Notice how the chain gets longer and longer and longer and longer. Notice how the boiling point becomes a higher and higher and higher and higher number. The longer the chain of the hydrocarbon, the higher the temperature it takes to boil the molecule. Now, we don't have octane on there, but if you put octane on here, it would, of course, be the 8-carbon chain because it's oct. I would bet octane, and you could probably Google this, I'm going to bet octane boils at around 110 degrees C, a little higher than the boiling point of water. And then if you went to nonane, which would be a 9-carbon chain, I'm going to bet nonane probably boils at around 170 or 150 degrees C. I don't even know that, but I would bet that just because as you increase the length of the chain, it's going to essentially take more and more energy. That's what temperature means. The higher the temperature, the more energy you're putting into the material. I'm going to need to put more energy into the material for a couple of reasons. One, the molecules are getting heavier, and two, because the molecules are getting more sticky. The bigger the molecules are, the better they have the ability to stick together. So the better they can stick together, that will be demonstrated by this increase in the boiling point temperature. Okay, so we're going to switch to my other slides. You know what I think I might do? Why don't we just stop there at this point, and on Wednesday we'll just start the next new lecture. But what I do want to say, before you disappear from me, remember to complete your test 2, part 3. It is due by 11:30 p.m. tonight. So please make sure that you go out there and do that. And then we'll just start lecture 7, which is a little bit more on these things. And we're going to move into some ideas about plastics for next time. So peace out till next time. Remember to vote.